In this video I'm going to talk about initial value problems. Now these are fundamental to what we're going to be talking about in the computational methods for ODEs unit. Okay, and when we talk about solving ODEs we often mean we're solving these types of problems, and these are given the shorthand IVPs. Okay, so in order to introduce this I'm going to just talk about a very simple ODE. Derivative of y equals y, which can also be written as dy dt equals y. So this is a separable ODE. So what I'm going to do is I'm going to put both the terms involving y on the left hand side. So we have dy over y, and if I multiply both sides by dt, I get dy over y equals dt, and of course to solve for this we simply integrate both sides. So the integral of 1 over y dy is the natural logarithm of y, and the integral of 1 times dt is simply t. What I haven't done here is, I'll just undo that quickly, I forgot to put in the constant of integration. So we got log of y plus, let's call it c1 for one constant, and we have t plus c2 for the other. Okay, so and I could rearrange this to give me log of y is equal to t plus c2 minus c1. So in order to solve for y, if I take exponents of both sides, okay, so that gives me y equals the exponential of t plus c2 minus c1, and using the laws of exponents this gives me e to the t times e to the c2 minus c1. So c2 and c1 are just simply constants. So what I'm going to do is, if I let k equals the constant c2 minus c1, so what we then have is y equals e to the t e to the k. Now e to the k is, because k is a constant, e to the k is also going to be a constant. So I'm also going to let c equals e to the k, and this gives us y equals e to the t times c. So this is the analytical solution of this ordinary differential equation up here. So that was quite a simple one, separable ODE, which we calculated, or we found the solution via analytical methods. Okay, so what does this solution mean? So here, if I was just to draw a quick graph, quick axes here. So I have a t-axis and I have a y-axis. So what we have here is a family of solutions. So whatever the value of c is, we're going to have a different solution. So one solution could be like that. If we have a different value of c, it could be like that. If we have another value of c, it could be like that, etc. So we got an infinite number of solutions to this ordinary differential equation. Now if we fix c, so if we, let's say we say c was equal to some value, or let's say some initial value y0. Okay, so this is when t is equal to 0. We're saying that c is going to be equal to y0. So therefore y is going to be equal to y0 times e. If t is 0, that's e to the 0, so that's just y equals y0. Okay, so what that means is we've set an initial value, let's say there, let's see if that's our y0, and what this means is we now have this solution. Okay, so out of our family of infinite number of solutions, if we set the initial value to be some known value y0, we then, instead of having a family of solution, we have an initial solution. Okay, so this brings us on to the idea of an initial value problem. So an initial value problem, it comes in three things, or three main things. We have some ODE, and the ODEs are normally written as this form. So this is, in this case, it's a first order ODE. We have a domain, so let's say we've got some minimum, so t is in the interval, some minimum goes from a minimum value of t to some maximum value of t, and we also have some initial value for y. So at t min we have some value, so let's say it's some value alpha. Okay, so what we have here is, this is our ODE. Oops, bit of a dark curly bracket there, but let's stick with it. This is our ODE, this is our domain, and this is our initial value. And this is kind of what an initial value problem is. So as long as you've got these three things, we can solve, as long as the ODE has a solution, we can solve using numerical methods.